continue the discussion on symmetries in crystals. We were discussing point symmetries in the last lecture, and now we talked about rotations. Today in this lecture I will talk about the other symmetry elements, the other point symmetry elements. In particular, I will talk about reflections, inversions and rotoinversions. So let's continue from where we left off last time. So in this lecture I will be talking about reflections, inversions and rotoinversions. So to remind you what we discussed in the last class, we said that there are point symmetry elements, and each symmetry element generates an operation, and we said that a point generates a center of inversion, a plane generates a reflection, a line can generate either a rotation or a rotation and a reflection, which is called a rotoreflection, or a rotation and inversion, which is called a rotoinversion. Now in the case of molecules, we usually use a rotation and reflection. So this in the case of molecules is called an improper rotation. And this is mainly used for molecules, for describing molecules, as opposed to solids where we use rotoinversions. This is used for solids. So for crystals we'll be mainly focusing on rotoinversions. We won't be talking about rotoreflection. Okay. So let's continue. So I've already talked about proper rotations. Okay. Now I will briefly summarize what we talked about rotations in the last lecture. We said that only two-fold, three-fold, four-fold and six-fold axis of rotations are possible, and there are two types of symbols. You can call it as Cn under the what is called the Schoenflies notation, or simply n under the Hermann-Mauguin convention. Okay. We will be discussing these conventions in more detail later on, but just bear in mind that there are two kinds of symbols. There is the Cn and there is the n. Okay. And what should be kept in mind is that one solid can have several rotation elements. Okay. It need not have only one rotation axis. So for example, we were talking about the tetrahedron. So we talked in particular about the silicon with the 4 oxygens forming a tetrahedron, and we identified, we said that the axis passing through any one oxygen atom and the central silicon atom. So it could be any of these. So these are all threefold axis of rotation. So each of these are C3 axis. Okay, but additionally we will see that there are also some C4 axis, and I will just show you what the C4 axis is, and then I will describe it in more detail. So or a C2 axis. There are also C2 axis. So there are two-fold axis. Okay, so it goes like this. Okay, and basically this is a C2 axis. So what is this? What is this C2 axis, and how do I understand it? So the easiest way to understand it is to look at a tetrahedron in terms of a cube. So a tetrahedron can be visualized as in the following way, using a cube. So you put the silicon atom at the center of this cube, and you put 4 oxygens at, so this is a representation of an oxygen at alternate corners of the cube. So you take a corner and then you skip one corner and go to the alternate corner, skip one, go to the alternate, and you do this, and you will get what you will get here is a tetrahedral arrangement around this central Si Si atom. So this is exactly the same structure as what we showed here. So if you visualize the tetrahedron this way, then we can easily see that this axis passing through the center of the cube and going through the central silicon atom and coming out on this side of the cube. Okay. So this axis coming out from this center, okay, is clearly a four-fold axis. Or sorry, it is a two-fold axis. So this is your two-fold axis. So this is a C2. Okay. You can see if I rotate by 180 degrees around this, the silicon atom stays where it is. This oxygen moves to this oxygen, and this oxygen moves to this oxygen. So you get an identical configuration. So clearly this is a C2 axis, okay, that essentially permutes these two oxygens and these two oxygens amongst each other. Okay. So what is important is that your tetrahedron has these 4 C3 axes and 2 C2 axes. Okay. And later we will see that it is the presence of these symmetry elements that will actually define the type of solid, okay, that is used to classify solid. So now let us go to the next symmetry element, that is a reflection, and we will again consider the tetrahedron because the silicon and 4 oxygens tetrahedron. And let me show this as a this one. So now you can, if you want to form a plane, okay, now you should notice that the point symmetry elements will all contain the central silicon atom, okay, because there is only one silicon atom. So then every symmetry element should go through that. So you can make a plane consisting of silicon and 2 oxygen atoms. Okay. So you can take this, for example, I could take a plane formed by taking these 3. So this oxygen, this silicon and this oxygen. Okay. So I would get a plane that looks something like this. This plane, this contains the silicon and the two oxygens. Okay. And this would be this plane consisting of this oxygen, this silicon and this oxygen would be a reflection plane, because if you reflect about this plane, then you can see that these 2 oxygens will change their positions. Okay. Remember that this plane is not perpendicular to the plane of this screen, because this oxygen is actually outside, it's coming outward. Okay. So now you can clearly, so basically what I want to mention is that you need 3 non-collinear points to define a plane. So if you have 3 points that are not all on a line, okay, then you can define a plane. So you need 3 points. So the silicon, the oxygen and this other oxygen, they together define a plane, and this plane turns out to be a plane of reflection. So this turns out to be a reflection symmetry. Okay. Similarly, you can also make a plane consisting of any other two oxygen atoms. So you could take silicon and any 2 oxygen atoms. Okay. So now the number of mirror planes okay. So you have 4 oxygens. Okay. Now 4 oxygens, and you have to choose 2 of them. Okay. So again it's quite easy to see. So you do 4. The number of ways of choosing 2 out of 4 is 4 into 3 divided by 1 into 2, that is equal to 6. So there are 6 different planes, mirror planes, that you can construct using this tetrahedron. in SiO4. Okay. This is again an important concept, that you can have several planes, and each of these is a plane of reflection, is a plane of symmetry, that is, it has a mirror reflection symmetry about this plane. Okay. Now, the symbols that are used for mirror planes in the molecular notation, you may have seen that there are terms like sigma v, sigma h, and sigma d. Okay. So, these are in the Schoenflies or molecular symbols, molecular group theory. Whereas the Hermann-Morget or the crystal convention is just to write it as an M. So, if you have a plane, you just write an M. If you have multiple planes, then you write it as M, M. So, that is 2 mirror planes. And so on. Okay. Now, so you can have these mirror planes in any crystal, and now let us look at let us look a little bit more detail about mirror plane. Now, there is a special case when you have this is a combination of reflections and rotations. Particular case, I'll take one example where, okay, let's take a simple 2D example. So if you have something like a, let's say an atom A at the center, and you have 4 B atoms. Forming a square with a square symmetry. Okay. Now, what you see is that if you look at so perpendicular to screen, okay, passing through A, there is a C4 axis. So, you have a C4 axis, and let me show it in this notation. I will put a dot and I will put a circle around this. Okay. So, this is your C4 axis. You should remember that it is actually perpendicular to the screen of the paper, perpendicular to the screen, and it passes through the point A. So, this is a C4 axis, and we also notice that there are various mirror planes. So, I will just show it in a dashed line. Okay. So, this again everything is perpendicular to the screen. Okay. Now perpendicular to the screen, passing through these 2 B's, you have a mirror plane. Okay. Okay. Now, what similarly you can also have a mirror plane in this way. You can also have a mirror plane perpendicular to this A. Okay. So now what we see in this is the following, that and you can also have mirror planes along this, and you can have mirror plane along this. Okay. And what we see is that these mirror planes are related by a C4 rotation. So, for example, if you take this mirror plane, I will call it 1, and rotate it, perform a C4 operation, okay, then you will get mirror plane 2. Okay. So, and similarly, when you take this mirror plane, I will call it 1 prime, and perform a C4 operation on it, you will get mirror plane 2 prime. Okay. And so, this is a general rule that when you have an n-fold rotation axis and a reflection, you will generate other n minus 1 reflections. Okay. So, just the existence of this one plane along with this C4 axis ensures that you generate this other plane. Now, it turns out that you could do the C4 again, but then you get back to the original mirror. You could do the C4 again, you get back to this mirror. So, in general it generates 4 other reflections. In this case 2 of them are the same as the other 2. Okay. So, let us take another example. Let us take a case where let us say I take A and I take AB3. So, I take AB3 . Okay. Now, this is a now you see that if you have a C3 axis going through A. So, you have a C3 axis going through A, this is a C3 and you have this mirror plane. Okay. Now, if I apply C3 on this mirror plane, okay, then I will end up with this axis, and if I apply it again I will end up. Okay. So, essentially if you apply this C3 twice. Okay. So, you start with 1, then you will end up with 2 and then you will end up with 3. Okay. So, you can see that this C3 and this 1, they ensured that you have two more mirror planes. So, this is a property that mirror planes are generally found. You find multiple planes, mirror planes, whenever you have a CN axis that contains that mirror reflection. Next, I will talk about inversion. Okay, and this refers to the center of inversion. Also it is referred to as center of inversion. So, some crystals have a center of inversion. Okay, and again we can look at the molecular description for this symmetry. Suppose I have an octahedron. Okay, suppose I have an octahedron. So, let us say I put A in the center. Okay, and I have B, this is actually coming out of the paper, and you have, so maybe I will just show this using dots just to show that it is going inside the paper and that this is coming outside. So, this B is coming out of the screen of the paper in 6 in so now you see that this A, if you invert about this A. Okay. So, if I call it if I label these B atoms as 1, 2, 3, 4, 5, 6, then what you see is that after inversion you end up with something that looks like A, and now the B that is here is a different B. So, now the B that is here, after you invert, then this 4 comes here. So, you have a 4 here and you have a 1 here, you have a 5 here and a 2 here, you have a 6 here and you have a 3 here. Okay. So, this is the effect of inversion, and the center of inversion. So, A is referred to as a center of inversion. So, there are some crystals like which have local octahedral coordination, which we will show a center of inversion. And now, similarly, a cube will also show a center of inversion. So, if I take a cube, So, there is a point at the center of the cube, okay, which is a center of which is an inversion center. So, the center of the cube is an inversion center. Okay. So, if I invert about the center, then this point will go to this point, this point will go to this point, this point will go to this point, and finally, this point will go to this point. Okay. So, the cube will get inverted along about its center. Okay. And so in the symbol for inversion, okay. So again there are two symbols. One is in molecular, for molecules we use which is the Schoenflies symbol is I, and this is for crystals we use 1 bar. So, 1 bar is the inversion about the center, as just as I is the inversion about the center for molecules. Okay. So, crystals that have there are crystals that have centers of inversion, and there are crystals that do not have centers of inversion, and in each of the case you will get different properties. Okay. We usually look at crystal structures that do possess a center of inversion, but there are often we look at those that do not have a center of inversion. Now, the last symmetry operation I am going to talk about is rotoinversions. Okay. Now, notice that I mentioned that we will not talk about rotoreflections. Okay. So rotoreflections or improper rotations, these are useful for molecules, used for molecules. Okay, but for solids we use rotoinversions. Okay. So, what is a rotoinversion? A rotoinversion is essentially a Cn rotation followed by inversion. Okay. So, or if you are using the crystallographic notation, you will say an N rotation followed by 1 bar. 1 bar is the inversion operation. Okay. Now, what does how does this work? Okay. So, let us take an example of this tetrahedron again. Okay. So I will look at the tetrahedron, and for convenience I will look at it using a cube. And I won't I'll just show the silicon atom in red at the center. So, the red is the silicon atom, and the 4 blues are the oxygen atoms. They are at alternate corners. I can choose any 4 alternate corners, and I will get my cube. So this is my silicate tetrahedron that we already saw, and we already saw that there is a two-fold axis of rotation that looks like this. It looks like this. So it passes through the center of one face, comes out through the center of the opposite face. So this is a C2 axis. Okay. Now, we can also see that this C2 axis, okay, is also a 4 bar axis. So, it is a 4-fold inversion axis in the following sense. So, suppose I take this suppose I rotate by 90 degrees about this C2 axis. Okay. So we will see it right here. So, let me draw the cube. I will draw the cube. I will draw it a little small, just So, we start with this, this, this and this, and oops, this should be in the rear corner. Okay, I'm not showing the well I can show it. Now, if I perform this axis, if I perform a C2, okay, then what it will, or C4 rather, if I perform a C4, okay, then let me label these atoms. So, let me label them as 1, 2, 3, 4. So, if I perform a C2, then what I will end up with is something that looks like this. I'll just or C4 rather. If I perform a C4, then this 1 will come down here, 1 will end up here, the 2 will end up at this site, okay. Now, the 3 will end up over here, and the 4 will end up over here. Okay. That is what will happen if you perform a C4. Okay, so a C4 will take it to this, okay. And then now if you do an inversion, if you invert about the center, then what you will get is again the silicon atom is at the center, and you can see this 4 will come to this corner, the 3 will come to the opposite corner, that is here, the 1 will go to its opposite corner, which is here, and 2 will go to its opposite corner, which is here, which is essentially identical to what we started with. Which is essentially the same as the starting configuration. So you can see that a C4 axis, that is a 4 bar axis, okay, that is a C4 followed by an inversion, okay, that is actually a symmetry operation. Okay. So, though this tetrahedron does not have a C4 axis, okay, it does not have a C4 axis, it does not have an inversion. However, it has a 4 bar or a C4I or a C4 followed by I. Okay. So, important is again that tetrahedron does not have a 4 axis, 4-fold rotation, that is 4 axis, or 1 bar, which is an inversion. Okay, it does not have a 4 axis or a 1 bar, but it has a 4 bar axis. Okay, so this is referred to as the inversion axis. Okay, it is referred to as the inversion axis. So this axis, the C2 axis is a 4 bar inversion axis. Okay. So it has the tetrahedron has a C2 axis and a 4 bar axis, or it has a 2 axis and a 4 bar axis. It does not have a 4 axis. Okay, that is important to realize. Now, just as we saw in the case of rotations that only 2-fold, 3-fold, 4-fold and 6-fold rotations were allowed for crystals. Similarly, the only inversion axes that are allowed are the following. So, you are only allowed 1 bar, 2 bar, 3 bar, 4 bar and 6 bar. Okay. You do not have a 5 bar because we said pentagons do not fill space, and 1 bar is nothing but inversion. 1 bar is just an inversion without any rotation. Okay. 1 bar is an inversion without any rotation. So, the only roto inversions axes are 2 bar, 3 bar, 4 bar and 6 bar. Okay. So, these are the 4 roto inversions that are allowed. So, with this we complete the whole set of point symmetries that are possible for a crystal. So, this will be the end of this lecture. So, in the following lecture I will start discussing about the different conventions. We have already been talking about them informally, okay, but I'll make it a little more formal and describe the conventions that are used to that are initially we will show how they are used to describe the symmetry operations, and then later on we will show how they can be used to specify the different crystal systems. Thank you.